So today's lecture is on ordinary differential equations. So this is Unit 13, Lecture 1. So solving ordinary differential equations is surprisingly straightforward in Python. Just like how we did for optimization, where we were minimizing and we were solving roots, all we sort of have to do is convert our differential equation into a Python function, either using the lambda keyword or defining a named function. And then we just sort of plug it into a solver and it gives us the answer. It's actually quite simple. It will seem very refreshing compared to your ODE classes. So before we get into how to convert ordinary differential equations into the Python form, we need to know a little bit of nomenclature about ordinary differential equations. Like, for example, what is ordinary and how do we describe the dimensions? So an ordinary differential equation means there's no partial derivatives and there are no boundary conditions, so only initial conditions. So essentially just normal dy dx kind of differential equations. And then we're going to use another word called first order versus second order versus third order. So the order means what is the highest type of derivative. So first order means first derivatives, second order means second derivatives. And obviously if you have a second order, you can have both first and second derivatives, and that's normally the case. So let's see some examples of first order differential equations. So this example here is showing the rate of change in concentration, so dc dt. And we're saying that the rate of change in concentration is proportional to the concentration. So this is an example of like a first order chemical reaction, where the speed of the reaction depends on how much of the reactant you have. So this could be something like decomposition. Another example that maybe you've seen in fluid mechanics is filling a tank at a constant rate. So the change in volume with respect to the time is a constant times time. So you're filling at a constant rate. Another example is, say you're filling a tank but it has a hole in the bottom. So you have a term here which is showing how much volume you've added. So you're filling it at a constant rate. Oh wait, is this a constant rate? If the change in volume per time is equal to kT, that means over time the volume is increasing. Yes, okay, so you're filling at a constant rate, yes. Okay, and then you have here an opening in the hole. And this basically says that as you add more volume, you have more pressure, and that pushes more fluid out of the hole. So this is the area of the hole, and then this is the pressure as a result of filling the tank. So this is filling a tank with a hole in it. This is filling a tank without a hole in it. So these are the kind of first order, second order, and then these are all ordinary because it's C is dc dt, not partial, del C del T. They're regular derivatives. So are there any questions on first order, second order, or ordinary? And actually, if someone could just say a word, like just want to make sure that I'm actually giving my lecture to people.
Hi.
Great, thank
Yeah,
you.
no problem.
Thank you, great. Okay. I think I probably mentioned this already, but I saw on Twitter like someone put a video of a biology professor giving a 45-minute lecture on mute, uh, and he like didn't have he wasn't looking at the class because he was like using a board or a little whiteboard. So I'm always paranoid that I'm gonna end my 60-minute lecture and realize that I wasn't on Zoom or something like that, or I was muted the whole time. So always good to check in. All right, here's some example of second order ordinary differential equations. So this is the ideal spring mass system. So we're saying that the second order or the second derivative of position with respect to time plus the position equals 0. So this comes about because this is acceleration. This is acceleration here. So if you rearrange it, it says like acceleration is proportional to the position. And that's kind of like if you pull a spring, right? The farther you pull a spring, the more force you have, which is the more acceleration you'll get. Here's another example of a spring mass system where you have dampening. That is, the faster the spring is moving, faster the mass is on the spring is moving, the more you reduce the acceleration. So usually B is negative here. And that just means that essentially there's some kind of losses in the spring that slows down or dampens the system, right? Because an ideal spring mass system here without this dampening term, it would basically run forever like a perpetual motion machine, right? It would just keep bouncing forever. But in reality, there's always some loss in the spring that can be just from friction. It can be heating inside of the metal coil, right, as it expands and contracts. So that accounts for things like that. And then maybe a more chemical engineering example is Fourier's law of heat conduction. So this says that the rate of, or the temperature gradient, the second derivative, the derivative of temperature gradient is proportional to the position. So this is if you have like a metal rod, and on one side you keep the rod temperature constant, and then the rod goes out to infinity. This just sort of describes as you move along the rod, what is the temperature gradient? How does the temperature gradient change? Okay, so those are second order, and we saw first order ODEs. And the reason why we need to be able to talk about the classification, is that in Python, it only can solve first order ODEs. So what we need to do is learn how to convert second order ODEs into first order ODEs and do some transformations. This kind of is like in the constraint problem, right? When we did optimization and we had constraints, we always had to make the constraints equal to 0. And we always had to make sure our inequalities were strictly positive. So we have to do the same kind of transformations on our equations to make them work for the ODE solvers. Okay. So here's sort of the recipe for solving an ODE in Python. We have to convert it to standard form. We'll talk about standard form in a minute. Then we need to convert that standard form into an equation in Python. And this is so these two things are kind of like what we did in optimization, right? In optimization, we had to turn, like if we were trying to solve an equation, we had to make it into a root form. Then we had to implement the equation in Python. Now there's a new step here, is that we need to create a grid of points where we want to evaluate the ODE. One thing about ODEs, right, is that they're like solving an ODE gives you a function. But in Python, we don't usually, like when we're doing numerical methods, we usually don't work with functions. We usually work with a grid of points, right? So we have to say which points we want to know the value of the function. So we have to tell Python where we want it to evaluate the ODE. So for example, in the spring mass system, we have to say which time points we want to know the value of the position. Okay. And then obviously, we have to then call the ODE integrator with our function, our grid we created, and then an initial value condition. All right. So the first step, converting to standard form. So the standard form is that you need to make your ordinary differential equation look like this. You need to have the first derivative on the left-hand side, and then an arbitrary function on the right-hand side. And you can turn any ordinary differential equation into this form. It's just sort of a matter of algebra. So let's see an example. So let's take a look at our chemical reaction example, right? We have dc dt equals minus rct. So this is already in standard form, right? The derivative is on the left-hand side by itself, and then everything else is on the right-hand side. So let's see how to do the second order ODEs. So let's see the spring mass system. So the trick that we do is that we take a second order one-dimensional ODE and we add a new dimension to it so that it becomes a two-dimensional problem. And then that will reduce it from a second order ODE to a first order ODE. So the trick is that the first dimension is our normal dimension, and the second dimension is the first derivative. So then by making the second dimension the first derivative, we can rewrite the second derivative as a first derivative of the first derivative. So basically we take all second derivatives and replace them with first derivatives of our new dimension. Okay. So then we have this this d2x dt squared, that is with a dx2 dt. So it's the first derivative or second dimension, right? So it's a second derivative, and it's a second derivative by taking the derivative of a first derivative. And then our x's are the same, right? The first dimension is x1 is still x. And so by doing this, now we have a first order ODE, but now in 2 dimensions. So this is probably the most difficult part of solving ODEs in Python, is converting the order to new dimensions. So if you had a third order ODE in 1 dimension, it would be a 3-dimensional problem. And if you had a fourth order ODE in 1 dimension, it become a 4-dimensional problem. Okay, so are there any questions about this so far? Okay. So then to write it in standard form, remember that we need to have the first derivative on the left-hand side. So it's now a 2-dimensional problem. So our first equation is going to be that the first derivative of x1 is equal to x2. Okay. And then the second equation is going to be that the second derivative, or the first derivative of x2, which is the second derivative, is equal to minus k times x1. So that's a rearrangement of this equation. So this is kind of the one of the consequences is that every time you add a new dimension, right? So we need to add another equation, right? So we have 2 dimensions. So all of the equations, so here we went from 1 equation to 2 equations, right? We had this 1 equation, and then now we have 2 equations. One of the equations is always a freebie. Like this expression here is just, this is our definition of the second dimension, right? By definition, the second dimension is equal to the derivative of the first dimension. Like we added a new dimension, and that new dimension was the first derivative. So one of these like standard form ODEs is always just a gimme. It's just what we decided to do. We decided to make a new dimension, and it was equal to the first derivative of the x coordinate. So that is just a definition of what x2 is. Like we chose that. And then the other equation, this is that's a restatement of the initial equation that we were given. Okay. So there we go. So now we've converted the problem to standard form, but it's got 2 equations now because it's a 2-dimensional problem. Okay, are there any questions on this example? Okay. So here's another example. So the Fourier problem we had here, second derivative of temperature with respect to position is equal to position. So again, we add a new dimension, T2, which is going to be the first derivative of temperature. So we have our normal temperature, it's just T1 now, and then we have T2, which is going to be the first derivative of temperature with respect to position. So then our original differential equation now becomes a first order. So this second derivative now becomes a first derivative of our new dimension, T2. And then because of our definition of what T2 is, we have the second equation. And so now we have our 2 standard form equations that define the ODE. Okay, so that's how we convert to standard form. So let's just talk about implementing them in Python. So remember that for optimization, our functions had to take in 1 argument, and that was the x value, and then they had to get back 1 value. That was the value of our function. And if we wanted to deal with multiple dimensions, we still took in 1 argument and gave back 1 variable, but just the variable and the argument became multidimensional. Now what's different about ordinary differential equations is that we now take in 2 arguments, where argument 1 is the dependent variable. That's the variable which is in the numerator of the derivatives. Then the second variable is the independent variable. So that's the variable which is on the denominator of the derivatives. And then we return the derivative of the dependent variable with respect to the independent variable. So in our case here, the derivative of the dependent variable with respect to the independent variable, dc dt, is equal to minus r times c. So that's what we get. Okay. Now I put in a little default argument here, And this is because I haven't really specified what r is, so I just added a third argument with a default value. So this is just, if I want to use this function, I can use it for different r's. That's all that I did there. Okay, so the difference between ODEs and optimization is that when you write the function, it should take 2 arguments. Now notice that C can be multidimensional, like this is for the 2-dimensional, 3-dimensional examples we're going to have, but T should always be 1-dimensional, our independent variable. Okay. Sorry, T should not be multidimensional. T should always be, T can be multidimensional, and so can C be. Sorry. These are both have to be the same number of dimensions. Sorry, no, I'm wrong again. They can be different number of dimensions, but the output number of dimensions has to equal the dimensions of x. Oh god, okay. You know what? I'm not even gonna say it. We're just gonna see from the example what it looks like. So in the example here, we have x is like the first argument here. Yeah, I think that t can only be 1-dimensional. I will have to check. I'm not sure. I don't think we do any examples in the class where t is multidimensional. Okay. So the spring mass system here, we have 2 dependent variables. We have dx1 and dx2. And let's see how we implement that as an equation. So we take in our x's, our current positions. Well, I shouldn't say current positions. Remember, the first dimension is the position. The second dimension is the first derivative of position. So we can think about x as our position and velocity. Then we have our time, which is our independent variable. And then we need to give back both derivatives. So remember that the derivative of the position is equal to x2. Or to put it another way, if you view the x1 as position and x2 as velocity, the derivative of position is velocity. Then the second term, this is the differential equation, and that says that the derivative of the velocity, or the second derivative of position, is equal to position times minus k, and that was this expression we got here. Okay. And then again, I just added a third argument with the default value for what we want k to be, just in case we want to see different kinds of examples. Okay, so are there any questions on implementing these standard form ODEs in Python?
In your array, does the first, like the 0 position represents the first derivative, or like or not like the first derivative, but like your equation for x1, and then for the second one is your equation for x2?
Yeah, so this expression here is this. So the first derivative of the 0th x, I've written them as 1 and 2 here, which might be confusing. So in Python, it starts at 0. So the first derivative of the first dimension is equal to the value of the second one. And that's because we said that our new dimension we're adding to the problem is the first derivative. So that's what this first equation tells us. And then the second equation is about that other dimension, right? So that came from the equation which said that the second derivative is equal to minus kx1. So I replaced that second derivative with the first derivative of our new dimension x2, and that is equal to minus kx1.
Okay, thanks.
Yeah, hope that answers your question. Any other questions about implementing these in Python? Okay. So here's another example of Fourier's law. So these were the 2 ODEs in standard form. So again, we have t, and now x is the independent variable, and our previous example, x was the dependent variable. And then again, our first derivative of our first dimension is the second dimension, or this is the second dimension, right? Because we're counting from 0. And then the second dimension's first derivative came from the equation. So the second dimension's first derivative is equal to the value of the independent variable. So you can kind of see the difference here, right? This is k times x, so this is k times the independent variable, whereas in the spring mass system, it was k times the dependent variable, right? So it's a little bit of a difference there. Okay. Now, one thing to note is that the reason I have this NumPy array over here is that these functions need to work with NumPy arrays. So if I were to not have NumPy array around here and I gave back these two values as a list, they would be a list and not an array. And then the ODE integrator could have trouble with this. So I always put MP array around them to make sure that the output is an array. So the input will always be an array, but if you start slicing it and making a list, this was a list here. That's what the score brackets say, is that these are lists. So I wrap it in a NumPy array to make sure it comes back as a NumPy array. Okay, so then once you have basically defined your function, we need to do two more steps before we can integrate. The first is to set up our initial condition. So I'm going to do the concentration example. I'm going to start at a concentration of 1. And then I need to choose where I want to evaluate it. So I'm going to evaluate my function from time equals 0 to time equals 5. And I'm going to evaluate it at 100 points. So I'm making a grid from 0 to 5 that contains 100 points. So then I call scipy.integrate ODE_int. Then I give my function, which takes in the independent dependent variable and gives back the derivatives. Then I put in my initial condition, and then I put where I want to evaluate it. And then it gives back what is the value of your dependent variable at the points at which you passed in. So then I plot, my x, which is time, and then my y, which is the concentration. So you can see that the concentration is a decaying exponential. And indeed, that is the correct. If you were to analytically solve this differential equation that we started with, it indeed is e to the minus t. Okay, so that's how you actually compute the solution to the ordinary differential equation. So let's see the spring mass system. So I just put the function, I defined it again here, just so we can have it all in the same slide. So for my initial condition, I now have two dimensions, right? I have to specify the position at time equals 0 and the velocity at time equals 0, right? I have to specify the position and its first derivative. So you can see here that, at time equals 0, my position is 1 and my velocity is 0. Notice how the tangent line here is 0, slope. Then I specify at which time points I want to look at. So I decide to go from 0 to t. Then I plug all this in. So I put in the equation. Then I put in my initial condition, which is 2 dimensions, because it was a second order ODE, so it became a 2-dimensional first order ODE. And I put in my time points. Now this is kind of a little bit of a tricky thing, is that what it gives back is it gives back a matrix with 2 columns. Column 0 is the value for the first dimension, and column 1 is the value for the second dimension. And then the rows are the time points, right? Now you could plot both, but usually in these problems, we don't ask you to plot the position and the velocity, we just ask you to plot the position. So I grab only column 0 because that second dimension was just added so I could solve the problem. So I ignore the other dimension. So I only want the position because I'm trying to find the position over time, right? And then this just says I want all the time points. So then I can plot this now. Okay. So that's a real common mistake people make, is that they will call ODE_int and get back all the points, and then maybe in the problem I ask you what's the position at time equals 5, and you report 2 numbers, the position and the velocity. Well, that's not the position, that's the position and the velocity. So make sure you pay attention to which is which. And then just as another example here, if we have the dampening, that adds this extra term here that depends on the first derivative. Notice x2, recall x2 is the first derivative. So then we can plug that one in here, and then we get this dampening. So like this is a spring mass system where notice that over time the amplitude of the spring decays. That's because we have this dampening term here. Okay, so everything else is the same, except for I think we do a little bit longer time. So we go from 0 to 100 with 250 increments. All right, and that's how you solve an ODE in Python. Are there any questions on this? All right. So just for kind of fun, we can show, this is just sort of a little example, right? So I made in my spring dampening system, my B, how much the spring is dampened, I can set that as a function. I can change that, right? So just as a little example here, I'm doing a for loop and looking at different B's, okay? So in the plot before I had 0.1, here is showing as I change B, how does that affect the dampening of the spring? So like notice with a B of 0.001, it doesn't really dampen at all. With a B of 1, it dampens really quickly, and a B of maybe 0.25, it goes up. So let's see how we make a plot like this. So we need a for loop over B's. So I decided to go from 0.001 to 1 with 5 increments. So it's approximately like, 0, then 0.25, then 0.5, then 0.75, then 1. Probably could have started with 0. I just decided to start with 0.01. And then to actually call the ODE integrator, I do a little trick, is that I have this function which takes these arguments k and b, and what I do is I wrap it in a lambda. So this is the normal function damp spring. Now I wrap it in a lambda, so I have a new function I'm defining, which still takes in the x and t, but it then just dispatches the x and t. It dispatches, it calls the damp spring, but it changes what the b argument is to bi. So inside of this for loop, we're going to change bi over time. And then so I wrap in a lambda this original function and just change what b is here. And then everything else is the same from before, except for in my plot, I add a label so that we can generate the legend at the very end. All right, so that's just showing you sort of a kind of a way you can, if you have a function that takes in multiple arguments, you can wrap it in a lambda to still get a 2-argument function. And this allows you to sort of change what the b value is. So like if you didn't have this lambda here, if you just called this function, right, that wouldn't make any sense because you're calling a function, right? But the ODE int needs to take in a function. Calling a function gives you its return values. So you have to put that lambda there to make it still a function. All right. So just to mention, the solver in the ODE integrator is called an LSOTA solver. And this is sort of a modern ODE integrator that can handle what are called stiff ODEs. So stiff ODEs are ODEs where you have like multiple time scales. So that could be where you have maybe a spring mass system with a very long or a very quick time, but maybe a long dampening. Or maybe you have 2 springs and one has a very short time and one has a very long time constant, or a long period and a short period. You can change which solvers use an ODE int. You can use like Runge-Kutta, which is a kind of a famous ODE integrator. Just want you guys to be aware that this is the ODE integrator that's used as LSOTA. Okay, so that's it for ODEs actually. I think it's pretty straightforward. You just need to be able to convert the ODE to standard form, and then it's pretty simple to solve them. And you'll be doing this a lot in your reaction engineering course, or maybe it's called kinetics, maybe kinetics and reaction engineering, something like that. So, are there any questions on solving ODEs in Python? Okay. If not, we're gonna take a quick break, and then we'll get into lecture 2.